Hi everyone, this is the Hungry Math Professor here, and today in this video we want to show something that I mentioned in another video where I was talking about. Well, I've had a series of videos where I've been talking about cardinality of sets, and then I have the Cantor's diagonalization argument where we show that the real numbers are not the same size of infinity as the natural numbers. And I had another video where I do Cantor's theorem, which shows that the power set of any set is always a strictly larger set. And I mentioned in that video that the real numbers are the same size of infinity as the power set of the natural numbers. And so I want to now show you that this is the case. But if you can't, you might have to watch some of those previous videos to make sense of this. So there's a video on power sets. If you didn't watch the video on power sets, you want to check that out. There's a video on Cantor's theorem where you'll see that, for instance, the size of the natural numbers is strictly less than the size of the power set of the natural numbers. And then you can continue that to get a hierarchy of sizes of infinite sets. Um, and also there's another video where I show you Cantor's diagonalization argument, which shows you that the natural numbers are a different size of infinity than the real numbers. And then what we're going to answer today is to show that both of these sets have the same size. So you haven't come up with a new size of infinity, at least not in that particular process. And it's interesting along the way when we do this because um, it will show several little techniques on how to compare sizes of sets and things. Okay. And nothing I'm going to do here is going to be completely rigorous in the sense that I'm not going to try to write down any like careful formal proofs. Instead, I'm going to try to just give you the ideas, and it's going to come in several steps. And anything that I do in this video, you could turn into a careful, rigorous proof, but I don't want to bog us down in the rigorous details in these videos. I want these videos to be more about just ideas. And if you like, you can make them more careful and write up a careful proof. And but I want to focus on the pretty ideas at the big picture level here. And so the first thing that we want to do is to start with the power set of the natural numbers. So forget about the real numbers for a second and just change the setting a little bit. So we're going to start with the power set of the natural numbers. Um, and for instance, like let's say I take this element in the power set of the naturals, right? So 2, 4, 5, 7, that is in the power set of the naturals because it is a subset of the naturals. Okay. And well, but I should be writing this differently. So, no, this is good. Okay. So because I used the element notation, this is good. And then I want to show you how to associate to each element of the power set of the natural numbers a sequence of zeros and ones. Okay. So how do I turn this into a sequence of zero and ones? Well, first of all, for each element of the naturals, I'm going to put a little blank space. Of course, I got to stop at some point, but let me just go up to 10. And then, so for each natural number, I have a blank space. And I'm going to put a zero or a one, depending on whether I include that element in the subset or not. So in this case, I did not include one, so I'll put a zero here. And I did include two, so I'll put a one. And I did not include three, so I'll put a zero. I did include four. I did include five. I did not include six. I did include seven, zero, zero, zero. And the rest of the sequence will be zeros because I did not include anything else. Okay. So the way of thinking about a subset is going to be transformed into zeros and ones depending on whether you include something or whether you do not include something. Okay, and so we'll call this sequence of zero and ones, which I can write now as 0, comma 1, comma 0, comma 1, comma 1, comma 0, comma 1, comma 0, comma 0, comma 0, comma blah, blah, blah. This sequence we're going to call S sub n in general. So where, oops, so where S of n is a sequence of zeros and ones. And n is a natural number, right? So the point is that this is S sub 1, S sub 2, S sub 3, S sub 4. In general, I might not know what each S is. The point is that I want to just convince you that for each element of the power set, I can associate a sequence S sub n of zeros and ones. Okay, so that's what this claim is at this stage in the proof, is that every element S in the power set of the naturals, which is a subset of the naturals, if I wrote it as a capital S, is equivalent to, or can be, yeah, equivalent to is a little bit, by equivalent to, I mean I can associate a buddy here, equivalent to a sequence of zeros and ones denoted S sub n. Okay. And again, I'm not going to give any kind of a formal proof here. I'm just going to give some examples and hope that you get the idea. So for the naturals is a subset of the naturals. So to that one, I associate sequence that is always one. And of course, the empty set is a subset of the naturals. And to that one, I associate the sequence which is always zero. And so let's just look at the even naturals. That's a subset of the naturals, right? To that one, I associate the sequence 0, 1, 0, 1, 0, 1. I just keep going back and forth to only get the even ones. Oh, what about multiples of 3? Well, that's also a subset of the naturals. So then I'd say 0, 0, 1, 0, 0, 1, 0, 0, 1. And of course, a simple subset like the one that only includes 1, it's just going to be 1 comma 0, and then zeros the rest of the way. And anyway, hopefully there's enough examples to show you that that's always the case, no matter what subset of the naturals you take. The point is that I can always think about it the way I did up here, which is to say that I just put a 0 if I include that element in the subset, and I put a 1, sorry, I put a 0 if I do not include that element in the subset, and I put a 1 if I do include that element in the subset. And that alone should convince you that we can do this. And so now I want to define a new set, which I'm going to call, for no amazing reason, just capital pi, which is going to be the set of all sequences. Normally the sequences are written with curly braces, where each S sub n is a element of 0, 1, meaning it's either 0 or 1, and n is a natural number. So this is the set of all sequences of zeros and ones. And what we've done here, or that's what I'm claiming we've done, is shown that the set pi has the same size as the power set of the naturals. Now, again, I didn't do any like rigorous proof here, but I think I gave you the basic idea, and you just might want to convince yourself that there's no repetitions here, that there's always a unique association. But again, if you go back up to the idea of either including something or not including in the subset is a matter of a 0 or 1, that you should be able to convince yourself that there will be no repetitions. And so to use the more rigorous language, you can show that there is a bijection between these two sets. And if you want, you can do as an exercise to show that bijection carefully. Okay, so now let's leave this claim aside. So this is claim 1. We're going to make 4 claims, and then when we put all 4 of these claims together, we will get the result that I'm after here. Okay, but let's put this claim to the side now, and let's change our thought process, and let's go and say the following. So we'll make a simple claim. We'll go to the real numbers now and say that the real numbers have the same size as the set of numbers between 0 and 1. Let me just define this in case you're not familiar, but this is just we call this the closed interval where 0 is less than r is less than 1, right? And oftentimes on the number line, we might draw this as the set of all elements between 0 and 1, right? And just shade it in. Okay, anyway, hopefully you get what I'm getting at here. I have to assume some notation when I do this, and I don't know what you all know or don't know, so I have to kind of just do my best to make some assumptions there. Um, and okay, so I want to show, first of all, a very simple claim, or maybe a surprising claim if you've never seen this, but it won't be that difficult to show. I'm just going to give you an explicit function here, which will do the trick. And the idea is that we're going to look at the function which is equal to cotangent of pi times x. And, you should remember that that's like cosine of pi of x all over sine of pi of x. And the point is that what does this graph look like, right? So if I look at the function, I only care to look at it between 0 and 1. At 0, this is going to go to infinity because you're dividing by 0, sine of 0 is 0. And at 1, this is going to go to negative infinity because cosine will be negative and sine will be 0 again. And at 1/2, this function is 0 because cosine is 0 at pi over 2. So what does the graph look like? It has an asymptote up here. It's going to go down, and then it's going to have an asymptote down here. And what you notice, if you remember, if you notice about this function is it's 1-to-1. It passes the horizontal line test. And so this is a bijection. So F is a bijection between, well, if you look at the domain, it's going to be 0, 1, not including 0, 1. And the range is going to be all real numbers because we have a vertical asymptote going to positive infinity at 0 and a vertical asymptote going to negative infinity at 1. So this is actually completely rigorous. This is a bijection between these two sets. And so we've shown then that the size of the open interval 0 and 1 is the same as the size of the real numbers. Now, given where I know we're going here, I actually want the closed interval. And here I will just kind of like quickly sweep this under the rug because it's a very simple fact. But if you have two infinite sets which have the same size and then you add 2 more points to it, you're not going to change the size. So the idea is that the closed interval 0 to 1 has the same size as the open interval 0 to 1. And we know that that has the same size as the real numbers. Okay. So I think I actually used this fact in another video, and I'm not sure if I showed you any justification for it or not. I forget. But if I didn't, then here it is. And if I did, then you get to see it again. But okay, that's the second point we need. Notice what I'm trying to do with this proof is, remember, we want to show that the real numbers have the same size of the power set of the naturals. And I'm working in from both sides. So in point 1, I've replaced the power set of the naturals with the set of all sequences of 0s and 1s. On the other side, I've worked in and replaced the real numbers with the closed interval between 0 and 1. Now, at this point, you don't understand why I did either of those things, but bear with me a little bit longer and you'll get the idea here. So here's point 3. So the point 3 is that every element in the closed interval 0 to 1 can be represented as a binary decimal. Now, what is a binary decimal, right? So I have to explain some things here. But again, we're going to try to work in and we keep replacing sets with equivalent sets of same size, and this will basically get us almost to the end. So what are we trying to do here? So every element in 0 to 1 can be represented a binary decimal. Well, first of all, a binary decimal will look like the following: 0.0, 1, 1, 0, 1, 0, 1, 0, so on and so forth. So it's a decimal. There's nothing before the decimal places because we're in the interval 0 to 1. We never need a number bigger than or smaller than bigger than 1 or smaller than 0. So we need nothing before the decimal place. Everything after the decimal place is going to be 0 and 1s. Okay. But in order to explain what this decimal even means, you always have to use fractions. So just like with regular decimals. So what does this decimal mean? Well, you take the first one, zero, the first decimal place, and you multiply it by a half. And you take the second one and you multiply it by 1 over 2 squared. And you take the third one, the third decimal place, and you multiply by 1 over 2 cubed. You take the fourth decimal place, multiply by 1 over 2 to the fourth. Um, the fifth decimal place, multiply by 1 over 2 to the fifth, and so on and so forth. Okay, this is, if you remember from regular decimals, though you may not have thought about regular decimals this way in a while, this is what you do with regular decimals, except you take 1 over powers of 10. Right? But here, if I want binary expansions, I'm going to take 1 over powers of 2. And now I have to somehow convince you, without going too crazy into this argument, I somehow have to just visually, I want to just visually convince you that no matter no matter number you pick between 0 and 1, I can always associate to it a binary decimal. Okay, so I'm just trying to give you a um, very basic visual argument. Okay, so here's how the visual argument's going to go. Let me just put a nice number line where on the left-hand side I'm 0 and the right-hand side I'm 1. Okay, and let me just pick out some random real number between 0 and 1. I'm just going to be very just pick that guy. So this is a real number, okay? But what I'm about to show you is not going to depend on which real number I choose. And so the process I'm about to explain to you will work no matter what real number I choose. And that's going to be my whole justification. And I'm not going to go into anything more than that. Okay. So here's the visual justification. I want to write R as a binary decimal expansion. So that's what I'm going to show that it's equivalent to that. And so here's how I'm going to do it. So I'm going to put a half down and I'm going to decide, is R to the left of a half or to the right of a half? Okay. Of course, it is to the left of a half. And so that means I want to put a 0 decimal place there. Because if I put a 1, it's going to force me to the right-hand side. I'm going to be into the fractions who are bigger than a half. And if I put a 0, it's going to force me to the left-hand side, the fraction which are smaller than a half. Okay. And then, depending on which side I was on, I'm going to put a further half. So I'm on the left-hand side, and so I'm going to put a further half. That doesn't look quite halfway, but anyway, take some liberties with my picture here. And I don't know, let's put it here, I guess. So that's a quarter, right? Because I did 2 halves. And again, though, R is to the left of that, so I want to put a 0 again. So that'll be 1 over a quarter. Now I do this again, I get an eighth. Okay, now I'm to the right of an eighth. So now I want to put 1 times 1/8 so that I am larger than that. And now let's say I go again, and let's say again, so this would be a 16th. So again, I'm to the right of 16th, so I want to add 1 times 16th. And then I do this again, and now I'm to the left of a 32nd, so I put 0 times 1/32. And I think if I do this again, I will be to the left again, and I'm going to stop here. Okay, so that means the decimal I would get is 0.0011000, and then I don't know what the rest is. Okay, and just to be clear, if I chose a different R that was like over here, for instance, I could do this again. Maybe I should call it R prime or something. So I could do this again and get a different. So now it would be 1 times a half because I'm on the right hand side of that. Then I would look at half of that, which of course is 3/4, but I'm still associating to it a quarter. It's to the right of that, so it'd be like 1 times a quarter. Then I do this again. It's kind of hard to tell. Let's just say it's on this side. So then we're looking at 7/8. So it's not about the numerator here. It's about so I'm at 7/8, but I'm not going to use 7 part at all. I'm just wondering if I'm to the left or the right. And since I'm to the left, I'm going to put a 0 times 1/8. And then I'm going to continue this. And it looks like the next two would be like this. And I'm going to stop there. Okay, so then this would be the decimal 1, 1, 0, 1, 1, and I don't know what the rest is. Okay. Beautiful. So hopefully now you're convinced that this will work. And the point is that if you keep doing this, you keep zooming in halves, eventually you will have to converge as the limit goes to infinity onto the unique decimal place. It's not entirely obvious. You could be a Debbie Dowder here and want some more rigorous arguments. I don't blame you for that. But that's not my goal in this video. I just want to give you the idea and I want to stick to that. So this is all I'm gonna say about this, but it is true. And it turns out that this works for any, it's not special about binary decimals. This is true of any decimal system you want. Like the regular decimals you're used to, you may never have asked the question, can I represent every real number this way? It's a funny question because how do you even define real numbers without understanding these decimals? You could define them. There's, anyway, I don't want to get into all this, but the point is that you can do this with base 3, base 4, base 5, and it's always 1 over that base to a power is how you come up with these. Okay? All right. So now I want to make the fourth claim, which I argue is the simplest claim to buy of all these, which is that the set of binary decimals, let's just give that a name. So let's say I call that fancy B. The set of binary decimals has the same size as the set of sequences of zeros and ones, which I called capital pi. So another way of saying this in shorthand is that the size of B, which is a set of all binary decimals, I should say the set of all binary decimals in 0 to 1. I'm not looking at binary decimals bigger than that or outside of that set. These are the same size. Now, this is not all that surprising because of the following observation, which is if you take a binary decimal, which can look like 0.01, 0.111, 0.001, 0.110, 0.001, blah, 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 and I want to associate to it a sequence of zero ones, well, there's a very clear way to do this. Forget about the decimal place and stick a bunch of commas in, right? So it's like 0, comma 1, comma 0, comma 1, comma 1, comma 1, comma 0, comma 0, whatever. It starts to get boring, but let's just finish this out here. Okay. And that's hopefully very clear that no matter what binary decimal there is, you can forget about the decimal place and stick a bunch of commas in, and then it's a sequence of zeros and ones, right? And these are basically the same set. And this is always unique because you can go back and forth, right? I could start with a binary sequence of zero and ones, forget about all the commas, and then stick a decimal place in the front, right? That's a way of showing that the notation goes back and forth, but because the notation uniquely stands for an element of each of these sets, this is a perfectly reasonable justification. And again, you can try to be more rigorous about this if you like. And now I argue that we can prove the entire thing by just putting all the pieces together. So putting together 1, 2, 3, and 4, these claims. Okay, so I'm going to put them together in a certain order. So this, like I said, the power sets of the naturals is the same size as the sequences of zeros and ones, which is the same size as the set of all binary decimals between 0 and 1, which is the same size as the closed interval from 0 to 1, which is the same size as the real numbers. These are all the same size, and hence, let's just make it really clear here at the end. The power set of the naturals is the same size as the real numbers. So there you have it. This is a nice, pretty proof where we just make a bunch of we make 4 different observations about sizes of infinite sets and put them all together. And hopefully along the way, you've observed, if you haven't seen these kinds of things before, several different tricks for showing that different sets have the same size, and these tricks can be used in different places, which is part of what we want to glean when we do these kinds of proofs in mathematics, is to observe some arguments that can be used in other places and new tricks in our toolbox. Okay, great. So like, comment, and subscribe. I hope you enjoyed this video, and I hope to see you at another video.